There is one caveat for the guidance from the previous clip, which applies if you're using factory-based middleware. In this demo, we'll learn about injecting services into factory-based middleware. I'll explain the difference between the two middleware approaches and how it affects registering and resolving dependencies. Factory-based middleware components implement the iMiddleware interface and are not activated by the conventional activation logic. Middleware inheriting from the iMiddleware interface is resolved by an iMiddleware factory implementation on a per-request basis with the help of the DI container. This allows transient and scope services to be injected via their constructors. In my experience, the use of factory-based middleware is pretty rare, but it's worthwhile spending a few moments to compare the differences. Returning to the middleware class we created in the previous clip, let's convert it to factory-based middleware. Before we do, I'll use Ctrl-Z to undo the previous changes, returning the user manager dependency to the constructor. The first change we need to make is to add the iMiddleware interface to the class. Using the Visual Studio tooling, I will implement this interface so that the method we require is stubbed out. Factory-based middleware receives its next delegate via the invoke-async method rather than via the constructor. We can remove this parameter from the constructor and delete the code used to assign it to a private field inside the class. We'll leave our two other application dependencies in the constructor. Scrolling down, the invoke-async method, defined by the iMiddleware interface, has a slightly different signature to the one we used for our convention-based middleware. I'll cut our code from the previous method and paste it in as an implementation for the invoke-async method defined by the interface. We need to make this method async since we await asynchronous code inside it. We can remove the original invoke-async method, which is no longer needed. Because our new method accepts a request delegate parameter, we can update this final line to use the next parameter to pass the request onto the next middleware in the pipeline. This completes our changes to this class to convert it to the factory-based middleware pattern. To see this in action, I'll add a breakpoint here. We should then visit the program file to register this middleware. Factory-based middleware needs to be registered manually with the iService collection so that the factory can later resolve it from the container. Because we are now registering the middleware directly, we can include a lifetime appropriate for the middleware. Because we depend on scoped services, we should register it using the try-add-scoped method on the iService collection. When I debug the application, no exceptions thrown, and the breakpoint in the middleware is hit. This happens twice as the browser has made two requests, one for the page and one for the favicon. After continuing through each of these by pressing F5, the page loads correctly. I rarely use factory-based middleware in my applications, but it's worth being aware that it's an option and it does provide more control over the lifetime of middleware components when desired. In ASP.NET Core, dependencies can also be injected into views. This includes both traditional MVC Razor views and Razor pages. In this demo, we'll look at injecting dependencies into Razor views. In our application, logged-in members can book courts through the website. As we've seen already, various rules exist to control which courts members may book and for how long those bookings may last. It would be helpful if the user interface indicated to the user what the maximum configured court booking lengths are. There are various ways to achieve this, and we'll look at one option that involves directly injecting configuration into our view for the booking page. Here is the Find Available Courts Razor file. To inject dependencies into this file, we can use the @inject directive. In this case, we'll require an iBooking configuration option to be injected. This will be resolved from the dependency injection container and acts a little like a property on the view. I'll name this injected dependency booking config, which is the name that we can then use to reference it from within our Razor code. Now that we have the configuration injected, we can use its properties to add a paragraph at the top of the page. Inside this paragraph, we'll advertise the maximum court booking time for regular and peak hours so that members understand the limits for their bookings. This is a straightforward way to inject and consume dependencies inside a Razor view. When we run the application and load the Find Courts page, the new paragraph is rendered at the top. While I've shown this approach for completeness, I generally recommend against the overuse of view injection. It tends to mix concerns, leading to business logic creeping into views where it doesn't belong. For something simple like accessing static configuration data, it can be convenient. It can be reasonable to inject services into views when the services are specific to the concern of rendering the view, such as localizing the content or populating drop-down lists with specific data. While it can be somewhat a matter of opinion, I advocate that a best practice is to prefer passing state into Razor views via the page model, as we did when rendering the membership advert on the homepage in a previous module. For several releases, ASP.NET Core has included a mechanism to register hosted services that can be used to perform long-running background processing, such as polling for data from a queue. In this demo, we'll learn how dependency injection can be used with a hosted service, and we'll discuss how to create scopes from which services may be resolved. To learn more about hosted and background services, check out my course Building ASP.NET Core Hosted Services and .NET Core Worker Services, where I dive into it more deeply. Rather than create a hosted service from scratch, we'll go behind the scenes and review the code for an existing hosted service used to set things up for the demo application. Inside the background service folder, I have an existing class implementing the iHostedService interface. This service sets up the database for the sample application. The start async method on all registered implementations of iHostedService will be called in sequence when the application starts. Any registered implementations of iHostedService are created when the application starts. The instances live until the application exits. As a result, much like conventional middleware, any services injected into their constructor are captured for the application's lifetime, so only singleton services should be directly injected in this manner. The initialized database service depends on the user and role manager classes and the entity framework DB context, all of which are scoped services. As a result, we can't inject them safely via the constructor. Instead, the constructor accepts an iService Scope Factory. An implementation of iService Scope Factory is registered internally in ASP.NET Core as part of the dependency injection container services. The start async methods of any hosted services are called when the application starts, and they must return before the application begins to serve HTTP requests. As a word of warning here, one should avoid any long-running work directly inside the start async method, as it essentially blocks the server until that method returns. This is a sample application and the logic here executes very quickly. The first line of code uses the injected scope factory to create an async scope. The scope implements iAsync disposable, so I've included an awaited using declaration, a feature available since C# 8, to ensure that it's correctly disposed of at the end of the method. Disposing of the scope will release any retained scoped resources and resolved services. Once we have manually created a scope, we can access its service provider and resolve services. This is known as the service locator pattern, where we resolve services directly from the iService provider. Wherever possible, avoid this, as it's considered a bad practice. Instead, always prefer injection into constructors or other supported methods. In this situation, we must use the service locator pattern to request the tennis bookings DB context from the scope. Once resolved, we can use these scoped instances as necessary. The startup logic here ensures that the database is created before seeding user data if none already exists. Creating scopes in this way is generally only required when we need the dependencies outside of the ASP.NET Core request lifecycle. Hosted services are the main example of where we may need to manually create scopes. Manual creation and crucially disposal of the scope inside this hosted service allows us to access the scope services correctly without capturing them into a longer lifetime than intended. I'll add a breakpoint inside this hosted service. Before we run the application, let's see how the hosted service is included in the application. Inside the program file, I have my internal setup region that we saw earlier. This line here adds the hosted service to the application. When I debug the application, we can see this because the breakpoint in the hosted service is now hit. The scope is created and is used to access the scoped services required to ensure that the database for this demo is seeded correctly. That's all we need to cover for the fundamentals of dependency injection into hosted services. Remember, I have a course specifically on hosted services and background services that you can view to learn more. Join me in the next module, where we'll conclude this course by learning how we can go beyond the built-in container. Welcome back. In this final module, we're going to discuss the options we have when the functionality of the built-in Microsoft container is not sufficient for more advanced situations that we may need to handle. We'll look at extending the built-in container with 2 extra features available in a third-party library called Scrutor. We'll use Scrutor to perform assembly scanning and apply the decorator pattern in the tennis booking application. When this still isn't sufficient for advanced requirements, we'll look at a final option to swap out the built-in container with one of the many third-party open-source alternatives. Scrutor is a fantastic library that fills 2 gaps in the functionality available in the Microsoft container, providing support for assembly scanning and applying the decorator pattern. Created by Kristen Hellang, the library is open source and available on GitHub should you wish to explore the code or raise issues. Releases are available as a NuGet package that can be referenced in applications to use its features. Let's add Scrutor to the tennis booking application. We can view and copy the package reference for the latest version on the NuGet website. Switching back to Visual Studio, we can double-click on the tennis booking project to open and edit the project file. We'll paste the copied package reference into this item group and save the file to trigger the restoration of the package. That's all we need to do to install Scrutor into the tennis booking application. You may, of course, install the package via the NuGet Package Manager user interface if you prefer.